Alright, this is NCCER Electrical 4 Revision 3 Heat Tracing and Freeze Protection Module, module number 26409-20. So, for a lot of you guys, if you're watching this class in Southeast Louisiana, this might be stuff that you might never use. But a lot of this you might never use, but you might end up using this all the time. So this is going to be, like I said, heat tracing and freeze protection for different stuff. Obviously, here in Southeast Louisiana, we do not get a lot of freezing temperatures and stuff like that. So there might be some stuff that we talk about that you will never see unless you move somewhere else. On the other side of that, this heat tracing is also used in areas where you have to, the process has some type of chemical or component that needs to be heated up to where it will move better. So all these oil refineries, you think of crude oil is usually a pretty thick substance. You might have to use like this heat tracing on these pipes in order to get this stuff at a more like a thinner ball or a thinner consistency in order to move it better. So you might end up using some of this stuff if you end up going to a refinery or something like that. So don't count this chapter out, but there's definitely going to be some stuff that if you stay down here in Southeast Louisiana, there's definitely going to be some stuff that you will never use. So I'm on page 1. We've got a ton of trade terms. There's going to be a bunch of different types of this heat tracing cable, and you're going to need to know the difference in it. So nothing highlighted, but like the constant wattage heating cable, you're going to need to know the mineral insulated heating cable, parallel resistance heating cable, power limiting heating cable, self-regulating heating cable, series resistance heating cable. All those are going to be different types of cables that are used for different reasons, and they have different functionalities and benefits and negatives and stuff like that. But you are going to need to know what they are and what the differences between them are. But nothing on page 1 is highlighted. Moving on to page 2, 110, piping heat tracing applications and materials. 110, page 2. First sentence in 110 is highlighted. The main reasons for using electronic heat tracing on piping are freeze protection and temperature maintenance of process fluids. So that temperature maintenance of process fluids is what I was talking about. You might put heat tracing on the outside of pipe in order to heat up the pipe so that fluids can pass more easily through the pipe. So heat tracing, very basic idea of what heat tracing is. If you guys are watching this and you have taken my instrumentation classes, you should this chapter should be pretty much a review for you. If you have not, you're just doing the electrical route. This might be something new for you, but heat tracing is used a lot in plants, and then especially a lot up north where weather is colder and stuff like that. You have the 3 main categories of heat cables. You got the self-regulating, the power limiting, and the mineral insulated. Those are the 3 bullet points right there at the end of 110, and then it's going to go into and give examples and talk about each one. So 111 is going to talk about self-regulating cables. Moving on to page 3, the whole second paragraph, or the first full paragraph, right after where you see the parallel resistance heating cable. That is all highlighted. So I'm going to read through this paragraph and then go back and tell you what to key in on. Self-regulating heating cables produce heat from the flow of current through the polymetric core or fibers. In both types of cables, the number of electrical paths between the bus wires changes in response to temperature variations. Keying in on these next 2 sentences. As the temperature surrounding the heater cable gets colder, the conductive core or fibers contract microscopically. This decreases the electrical resistance and creates numerous parallel electrical paths between the bus wires. So as the temperature goes down, the electrical resistance of these wires is decreased. Increased current flows across These parallel paths producing heat that warms the core or fiber along the length of the cable. So, it's just Ohm's law. If you're looking up here on the board, Ohm's law. Voltage is equal to current times resistance. So if I have the same voltage, we'll just say we have 120 volts, and I have a resistance and a current. So if my, we'll start off with very basic numbers, and we'll just say we'll have 50 amps and 2 ohms of resistance. All right. So if we have 50 amps, 2 ohms of resistance, no, that can't be right. We'll say, just for easy math, we'll say 12 amps, and we'll say 10 ohms of resistance to start off. So 12 amps times 10 ohms gives us our 120 volts, right? So if our resistance decreases, so say our resistance goes down to, we'll just say 5. So our resistance is 5, so then we have to figure out what our current is going to be, or what's going to happen to our current. So get rid of that. All we do to find our current is divide by 5. So we divide by 5, cancels out, divide by 5, and we get 24. Current is 24 amps. So we doubled our current. This isn't a reality because this is crazy high. But you can see as our resistance goes down, our current goes up. As current goes up, current produces heat. Heat is transferred to the pipe. The pipe stays warm. Fluids flow more freely. So that is how a self-regulating heating cable works. So as the temperature goes down, resistance goes down, current goes up, heat goes up. 112, power limiting cables. Power limiting cables, I've got kind of a weird highlight. I have one highlight, and it is the first sentence of paragraph 2 and paragraph 3. So you got 2 sentences and one highlight to go with them. So 112, second paragraph, first sentence is the power limiting heater cable. Figure 4, or what's up on the board, consists of a coiled resistor alloy heating element wrapped around 2 parallel bus wires. So you can see the bus wires up here on the board, nickel-plated bus wires, and then you can see your power limiting heating element. So the heating element is a coil wire going around those cables. Next paragraph, first sentence is highlighted. The resistor alloy heating element used in power limiting cables has a positive temperature coefficient, or PTC. This means the resistance of the heating element increases as the temperature increases and decreases as the temperature decreases. So it's just saying it gets hotter. As the resistance goes up, as it increases, which means current flow goes down, and then very much the opposite version, or the opposite of that. Moving on to the next section, mineral insulated cables. 113. All I've got is the first sentence of 113 highlighted on page 4. Mineral insulated cables are a type of constant wattage series resistance heating cable. Moving on from there, I've got nothing highlighted on page 5. I've got 114 long cable installations. You might have to splice this stuff. Some of this stuff is only regulated for certain lengths. You might have to split it up into more circuits than just one, covering various different distances based on the type of cable. Heating cable components and accessories. I've got nothing highlighted in, but you will see figure 7. Figure 7 is going to talk about all the different components, and you're going to get this picture right here that's on the board. So this picture is on page 6, and I've got a couple highlights off of figure 7 on page 6. I've got in the legend, I've got the power connection highlighted, and I've got number 6, the end seal, highlighted. So all the way at the beginning and all the way at the end. Both of these are highlighted. You'll read through this and go through what the different components are and how they work together and what they are and what they look like, stuff like that, because I can definitely see them pulling more questions off of this figure 7. So that's all the highlights that I have for 115. So I'm on pages 6 and 7. 116 and 7 I don't have any highlights for, so I'll be looking for highlights as you guys are taking this test for the first time, but no highlights on those. Heat tracing system control 120. So how is all this controlled? You're going to have control methods, page 8. You're going to have 5 different control methods: self-regulating, ambient sensing, proportional ambient sensing control, line sensing control, dead leg control. So those are all different ways to control, and then different things that are monitored in order to deal with control would be that next set of bullet points, which this isn't highlighted, but it is good to know. So most widely monitored system characteristics, you can do it by using ground fault, which is sensing for current leakage, continuity to make sure that you have a connection from one end to the other, current, which would be another way of using CTs, and then temperature, just using temperature in order to go up or down. 122. Ambient sensing control. So you can see this controller right here. This tube on the side is what is actually measuring the temperature of the air. So this controller controls based on the temperature of the air that's around it. So this drops below a certain temperature. This turns on. So this is only an on or off component. Excuse me, but can also be used to turn multiple circuits on or off. But this is just sensing ambient control, not the actual temperature of the pipe itself. But no highlights directly in that. Line sensing control, kind of the same, looks a little bit different, but you have your temperature bulb right here, and this goes on the pipe itself. So you are sensing the actual pipe temperature. In 123. Second paragraph, I've got the first 3 sentences highlighted, keying in on the last one. A PASC, proportional ambient sensing control, uses a programmable electronic controller connected to remote temperature input modules and contactor control modules to regulate one or more heat tracing cables. The PASC system monitors the ambient temperature and operates to continuously adjust the heat input to compensate for heat loss that occurs during the changing ambient temperature conditions. Key in on this next sentence. In order to maintain the desired temperature, a program algorithm calculates the cycle time to which the heating circuits are energized. So this thing can do some learning. But it can control multiple devices just like the ambient sensing control one. But like I said, this bulb is on the pipe itself, so you know what the actual pipe is. Line sensing control 124. I messed up. 123, proportional ambient sensing control. I was wrong. That is not this one. It looks more like that one, but it looks like this, except it has some control, so it actually watches the temperature to see if it's going on and off, and then it can create an algorithm that will turn heating circuits on and off based on what it's been for the last few days. Sorry. 124, line sensing control. That's where the line sensing control, that's where you're actually putting this on the pipe itself or the line, and you're actually measuring the temperature of the pipe. The first sentence of 124, line sensing control, is highlighted. A line sensing control uses a mechanical thermostat or electronic controller to measure the actual pipe temperature, not the ambient temperature surrounding the pipe. So whereas 122, the ambient sensing control, and 123, proportional ambient sensing control, that's just measuring the temperature of the air. This one is measuring the actual temperature of the pipe. 125, dead leg control. I don't have anything highlighted for that, but that's where you just have a pipe by itself filled with some type of fluid that is the same as what's flowing through the pipe, and they just use that pipe to determine, they're making a basis for temperature correction or temperature control for the whole pipe based on maybe like a 10-foot section of pipe that is just filled with that oil or gas or liquid, whatever it is, and then sensing the temperature of that and then making a determination for the system as a whole. Nothing highlighted dead leg control. 126, ground fault monitoring. The first sentence of 126 is highlighted. Ground fault monitoring. Ground fault monitoring system monitors the current leakage from the system heating cable, power wiring, and components to the ground using ground fault or leakage circuit breakers and or current sensing devices that measure current. This is figure 13 at the bottom. So everybody in this class should know how GFCI works. So essentially you got your hot side and then your neutral coming back, and then a CT or control transformer is looped around both of those, which should be reading 0, because whatever current is going out should be the current coming back. Whenever there is a difference in current, the GFCI will trip. So this is to make sure that that something's not happened, and wire's not broken, and current's not going to ground or to the pipe or something like that. This is not for personal or personnel protection. GFCIs in your house, I think, trip between 3 and 5 milliamps. These, I think it says, is at 30 milliamps. So this is a lot higher. You use these GFCIs to protect components, not personnel. So it's going to be a higher rating for when this will. There's not going to be nuisance tripping and stuff like that. Or there shouldn't be nuisance tripping with stuff like this. But yeah, that's how it works. 127, continuity monitoring. First sentence is highlighted. Continuity monitoring verifies that voltage is present at the end termination of a heat tracing cable run. So that's figure 14, or what up here on the board. You got the end seal with the light. So usually if your light's on, your power's good all the way to the end, which is just telling you that the cable is good. You can also have a transmitter that's sending something back to an operator or something like that, telling you that there is continuity or it is a complete circuit from beginning to end for that. Current monitoring, temperature monitoring, I don't have any highlights in those, but you can see figure 15 and 16 on page 12 is covering the current monitoring and the temperature monitoring aspects. No highlights on page 11. 130, heat tracing system operation. All right, so the last paragraph on page 12, the whole thing is highlighted. You need to know how these power line carrier technology, you need to know how it works. That's why I highlighted the whole paragraph, and you need to know what the advantage of it is. So 130, last paragraph on page 12. In some systems, temperature monitoring systems are communicated to the controller by means of power line carrier technology. In such systems, a power line interface unit, PLI, receives temperature and continuity inputs transmitted over heat tracing circuit power wires from special end-of-the-line heat cable circuit transmitters. Power line carrier technology uses frequency shift keying to encode digital data on the power line network. Digital ones and zeros are transmitted by coupling high-frequency signals onto the heat tracing bus wires of the AC power line. Key in on this next sentence. The use of power line carrier technology allows temperature and continuity data to be sent to the controller without running additional wiring to sensor locations. Figure 18 shows the wiring for a typical system using power line carrier technology to transmit temperature and continuity status. So, you can see up here on the board, you've got your two wires, your line and your neutral, going out and connecting to your heat tracing system, and then off of that, you at a different frequency, you can run information, ones and zeros. So all y'all should know that in the United States we run frequency at 60 hertz. So on these same wires at a separate frequency, they are running communications. So that allows us to run just two wires for power and communication. That is the power line interface technology that does this. Very important. They talked about this back when I was in college. I'm surprised this isn't bigger technology. When I was in college, they talked about this as far as I could plug my TV into the wall and I could get cable through an electrical outlet on a different frequency than was powering the TV. Not sure what happened to that technology, but I haven't seen it around. But it is used in this heat tracing systems. 140, equipment selection and installation for pipe heat tracing systems. Whole first paragraph is highlighted. The design of a complex pipe heat tracing system and the selection of its components requires extensive knowledge of the industrial processes and the process fluids used in numerous industries. For this reason, the design and component selection for a pipe heat tracing system is usually performed by a qualified master electrician, engineer, and or the heat tracing product manufacturer's engineering representative. So it's got to be somebody that's qualified in order to do this. This isn't going to be Joe Schmo off the street that decides that he's just going to put a piece of heat tracing around a pipe and call it good. Like this has to be designed. You also need to know down there below that, step 1. I only have step 1 highlighted. The step 1 of this process is to determine the application. Determine, another word that I wrote above that is identify. So either identify the application or determine the application. Find out what you want to do. Like if you're just doing freeze protection, temperature maintenance, or both, like those are very different things that are going to have different components and different aspects, different controllers. So you have to first determine what you want to do and how you want to do it. Moving on from there, on page 14, right after step 6, I've got that last paragraph before 150 at the bottom left of page 14, the first sentence is highlighted. The minimum number of circuits required for an installation is determined by dividing the total length of the heating cable needed for the job by the maximum circuit length that can be used for that particular type of cable. So you got to go find your cable, see how long it is and how long it can be for certain circuits, and then you have to divide based on that. Installation of heating cable and components, 151. Second bullet point on the page. The first two sentences are highlighted. All right, this is a weird highlight. I got 2 highlights for one question on different pages. This is going to be confusing, but just hang with me. So part 1 of the question is from the first couple sentences of that second bullet point on page 15. To verify that the heat cable has not been damaged during shipping, test it for continuity and electrical insulation resistance. Test the insulation resistance between the cable and conductors and the metallic grounding braid in accordance with the cable's manufacturing instructions. Flip it over to page 17. And the second bullet point on 17, first sentence, goes along with that highlight. After the installation is complete, retest the cables electrically the same manner as pre-installation testing. So all they're saying for that highlight going back to 15 is you're testing the cable for continuity and electrical insulation before installation and after installation. Just want to make sure that you guys know that. Next bullet point on page 15, all the way second to last sentence on the page is highlighted. Generally, 2 feet of cable is added for each electrical power connection, splice T, or an end seal. So you're adding 2 feet. And that's in case you got to do another splice or something like that in the future. but for each splice, T or end seal, you're adding 2 feet. Moving on to page 16. I've got the whole note on page 16 in the top left highlighted. If the heating cable is spiraled or wrapped around the pipe instead of being installed in a straight run, additional cable length must be allowed per foot of pipe. The amount of additional cable depends on the pipe size and the distance between the spirals. Key in on this next sentence. For a given pipe size, the amount of cable and the distance between the spirals, called the pitch, is determined by multiplying the pipe length by an appropriate spiral factor. Equipment manufacturers normally provide tables in their installation instructions that give spiral factors and cable lengths to add per foot for the different sizes of pipe. So if you're spiraling around a pipe, you're going to have to add, that takes more wire, and you're going to have to multiply that pitch by the length to determine how much extra wire or heat tracing you're going to need. So this is all before installation. During installation, those next set of bullet points on page 16, in the top right of page 16, I got the first sentence of that bullet point up there highlighted. Attach the heating cable to the pipes using fiberglass tape, aluminum tape, or plastic cable ties per the manufacturer's instructions. So that's fiberglass tape, aluminum tape, or plastic cable ties. That's how you're attaching this stuff to the pipe itself. You can see on page 17, wrapping a pipe around a valve. So you can see, for you guys that haven't taken instrumentation or just need a review, going around a valve, you're going to leave a big space like that, and that way you can go around it and bring this up around and bring it up here. If this valve was ever to have to be taken out of service, you can undo this glass tape and then leave this big slack of heat tape in the floor, take your valve out, replace it, and then put the heat tape back. If you pull this tight and wrap it around here and keep going, you're going to have to pull off the entirety of the heat tape and then change your valve and then put it back. This allows for maintenance of valves. You can see how it's on right here. Same thing for a flange. This goes down and around. If I ever have to replace, like this flange looks like it has an orifice plate in it, I can unwrap this, let the slack hang, change my orifice plate out, and then rewrap it, put my glass tape back. My insulation is good to go. On page 17, right after that highlight that you have in the second bullet point, the following considerations must be satisfied when installing sensors. So these are the actual sensors on the pipe itself. The third bullet point in the top right of 17 is highlighted. Sensors must be located 3 to 5 feet from any heat source or heat sink in the system. You don't want your sensors next to a heat source because it'll give a false reading of the entirety of the pipe. So you want it 3 to 5 feet away from any type of heat source. Moving on to page 18 and 19. They have 152 talks about the installing the insulation itself and stuff like that. You can read through that if you want. I don't have any highlights in that. But most of the time this is all encased in some type of insulation. NEC requirements for heat tracing. 153, first bullet point on page 19 is highlighted. Branch circuits and overcurrent devices supplying the equipment shall be sized at not less than 125% of the total heater load per the NEC. All that's saying is this is considered a continuous load. So you have to take whatever your load is, say your load is 20 amps, you have to multiply that by 125% and actually size your overcurrent devices, which is your circuit breaker and stuff like that, for 25 amps rather than 20 amps. You have to size up because this stuff is considered continuous duty because it's going to be, it has the ability to be on for 3 hours or more at a time. You'll have section 1 review questions on page 20. I recommend going through and answering these. I know you guys have the answers in the back of this chapter, but these are worth, these questions are good. Section 2, roof, gutter, and downspout de-icing. If anyone gets to a point in their life where they're having to install gutter freeze protection, and you remember this lecture, please text me and let me know that you use this because this section I'm going to run through fairly quickly because I don't think that it's going to apply to anyone that lives in this area. So obviously, if you look at this picture on the board or your page 21, you can see where those gutters have filled up with ice and snow. And ice is water weighs about a little over 8 pounds per gallon. So as that stuff fills up in your gutters and stuff like that, that can be a lot of weight. You don't want it in there, especially a lot of places don't want icicles, especially like businesses and stuff like that, that are higher up, because you don't want that stuff falling and hitting somebody. So you put in heat tracing to make sure that everything stays thawed out in your gutters and downspouts and stuff like that. It can also, like ice can also expand and break a lot of stuff as well. So system components and control 210. You're going to have 3 different types of control. Manual control, so that's just turning it on or off. Ambient thermostat control, so you can set it to a certain temperature, and then automatic moisture temperature control, which is going to control itself. My first highlight, you're going to have a couple questions come out of the first sentence of the last paragraph on page 21. The most energy efficient method of roof de-icing system control is an automatic moisture temperature controller. That is the most efficient. Moving on to page 2, they're going to show this picture on page 2 of all the different components. I want you to highlight figure 21. So components of a typical roof gutter and downspout de-icing system. You need to know what the controller looks like. So that is number, no, it's not, they're not numbered, but the controller right here on the right hand side, you need to know what that looks like. Like the controller is just going to be hooked up somewhere with the heating cable. I also have the T-kit highlighted. So where they have one wire running at the base and around this dormer and stuff like that to keep ice and snow off of the last few feet of the roof, and then they tee off and go into the gutters and up the valley and then through the other gutters and down the drain spouts. So they go from 1 wire to 2 wires, but that's where stuff is teed in, and this is where a T-kit would be. You need to know what a T-kit looks like. So controller and T-kit is what I have highlighted, but it would be a good thing to know what all of these are. You should read through and figure out what all of these are. They go through the installation of this stuff. I don't have anything highlighted in the steps of installation, but if you go to page 23, 221, installation of heating cable and components. The last bullet point, this is, they split it up again prior to installations, the first 4 bullet points, and then after the installation progresses, so this is as you're installing it. Last bullet point on page 23, last sentence. Leave drip loops where appropriate. Also be sure to leave a drip loop at each component so the water will not track down to the heating cable into the component. So that's saying where you have, if I zoom in here where my T-kit is right here, I would want to leave a drip loop. And that's to where the water will not go into, I don't want water inside of this T-kit where this stuff should be sealed off and stuff like that, but everybody knows water finds its way into stuff. But you can also see where they left drip loops down into here, so as stuff melts, water is right here rather than sitting on the cable or trying to get somewhere else. You're just putting drip loops where you want water to melt off to, and you don't want water to melt off into your different components. Page 24. Second bullet point's highlighted. Use UV resistant cable ties whenever you require 2 heating cables to stay together. So you can see, well, if you're putting cables together, I wonder if you can actually see. I don't see any cable ties in this picture, but UV resistant. Usually that means the black ones. The black ones are usually the UV resistant cable ties or zip ties. So if you're putting 2 cables together, you can use those zip ties or cable ties. UV resistant though. 222, the NEC requirements for this stuff. I've got the first bullet point in 222 highlighted. Braid circuits and overcurrent devices supplying the equipment shall be sized at not less than 125% of the total heater load per the NEC. Same thing as heat tracing. It's going to be considered a continuous load, so it's sized at 125% of the load. The third bullet point, the top right of page 24, is also highlighted. The external surfaces of any equipment that operates at temperatures above 140 degrees Fahrenheit shall be physically guarded, isolated, or permanently protected to prevent contact with personnel. So if this stuff on your roof is getting hotter than 140 degrees, it has to be guarded or isolated. Just make sure to where people aren't going to touch it. Touch something that's 140 degrees, it's going to burn. That's all I got for section 2. I'm going to move immediately into section 3. Snow melting and anti-icing systems. So again, this stuff is not used down here in South Louisiana, but you might end up moving somewhere where it is. I know back where I'm from in Tennessee, this isn't everywhere, but like nicer neighborhoods and stuff like that, like they put this stuff in their driveways to where they don't have to shovel their driveways. They can just turn something on and the snow melts off the driveways. But in different places, you can see in this picture, this is an actual bridge. So this is a, man, looking at that car, this is a bridge from the 1980s. But you can see how if you have a sloped bridge and stuff like that, you don't want ice and stuff on that. Like this could be from like Minnesota or somewhere crazy up north where they're not going to get a day where everything's going to melt off. Like it could be 20 degrees for a month and a half there, and snow's not going to melt. So the municipalities put in this stuff to melt the snow so people aren't sliding all over the place. 310, snow melting and anti-icing system components. I've got the third sentence in 310 highlighted. They are installed in a serpentine pattern with 1 foot spacing between the loops, securely fastened to rebar or wire mesh, and then completely encased in concrete. So you can see they're installed in these spiral patterns, and then you need to know that they have 1 foot spacing in between the loops. Key in on that, 1 foot spacing. Right hand side of page 26, that last paragraph on the page, the first sentence is highlighted. The most energy efficient method of control is automatic snow controller working in conjunction with a snow sensor. So you can see that snow sensor. If anybody sees one of these ever, let me know. We'll make sure I'm not teaching this for no reason at all. But they're saying the most energy efficient method is to use one of these automatic snow controllers with a snow sensor. So that's this system right here. The last sentence of that paragraph is also highlighted. Last 2 sentences of that paragraph going into page 27 are highlighted. An off-delay timing function incorporated into the controller can be used to extend the melting time. It keeps the melting equipment in operation at for a preset time after the sensors no longer detect precipitation accompanied by below freezing temperature. All that is saying, it might say like stay on for an extra hour or something like that to make sure you get all the residual snow melted off the driveway. Moving on to pages 28 and 29. Page 28 goes through the component selection and installation steps. I don't have anything highlighted that, but if you go to page 29, 321, installation of heating cable and components. So these are the heating cables. So these are still what gets hot and heats up the concrete, which melts the snow or ice. 321, installation of heating cable and components. I've got that first paragraph, last 2 sentences. It's about the second half of the paragraph. The minimum amount of heat cable required can be calculated using the following formula. Typically, 3 feet of additional cable should be allowed for making power connections. That's what you want to key in on. Whereas your heat tracing, 2 feet were used for splices and tees and stuff like that. In heat cable, in this heat cable stuff, your 3 feet of additional cable should be allowed for making power connections. 1 foot for a splice and then 1.5 feet for each connection. But key in on the 3 feet for making power connections. Moving on, first bullet point, first 2 sentences down below that are highlighted. Install the heating cable in a serpentine pattern, covering the area to be heated. Space the cable in accordance with job specifications, typically 1 foot on center. So that's just saying it's 1 foot from one to the next. 1 foot from here to here. Excuse me. Next bullet point is highlighted. Do not route heating cable within 4 inches of the edges of pavement, drains, anchors, and other objects in concrete. So you're keeping that thing 4 inches away from that. The next bullet point is also highlighted. Install the heating cable 1.5 to 2 inches below the finished surface and fasten it to reinforcing bars or wire mesh. So it needs to be closer to the top, but 1 to 2 inches below the surface. You can see as they're pouring the concrete on this, this will be 1.5 to 2 inches below the surface of this concrete. NEC requirements for this stuff. First sentence is highlighted. NEC Article 426 covers the requirements for all fixed outdoor electric de-icing and snow melting equipment. So that's for outdoor stuff. Section 426. Page 30. Second bullet point on page 30 is highlighted. Spacing between embedded or adjacent cable runs depends on the cable rating, but shall not be less than 1 inch on center. So it can't be less than 1 inch, but more likely it's going to be more than that depending on the cable rating. That's all I got for section 3. Moving directly on to section 4. Section 4, still got quite a few highlights in section 4. Other tracing and warming systems. 410, domestic hot water temperature maintenance systems. 410, the first sentence, you're going to have a couple questions come out of the first sentence of 410. Electrical heat tracing can be used for temperature maintenance of domestic hot water in lines wherever the hot water circulating loop is expansive, such as hospitals, schools, prisons, and commercial high-rise office buildings. So that's just saying you might have, like in a high-rise building, you might have the boiler in the basement. By the time it gets all the way to the top, that water's not as hot, so you can use heat tracing to heat that water back up so it's not cold for the people that live up in the top of the building. Something along those lines. Like that's where they're saying that you can use this stuff. 411, component selection and installation of this stuff. Last paragraph on page 31. The second sentence, I've got the second sentence highlighted. The heating cables are typically installed on copper tubing beneath fiberglass insulation. Most of the stuff is on copper tubing. It's not going to be on your PEX lines. The last sentence of that paragraph is also highlighted. Leave a service loop of extra heating cable at connections or at places that piping where the future service is expected. So you are leaving a service loop of extra cable where there's connections or at places where future service is expected. Page 32 and 33. They've got the NEC requirements for this stuff. Floor heating and warming systems. So this is usually done with like hot water and stuff like that, putting hot water through the floor. I've seen people do this in houses up north. These are usually in the nicer houses and whatnot, but you can see that guy having the mat down on the floor, so you can see the tubes running through this, and then they're running a layer of probably not thin set, but mortar or something through all of this, and then they'll come back on top with concrete or their flooring This might just be floor leveling stuff, but the water just runs through your floor and heats up your floor in whatever rooms you have. I have no highlights on pages 32 and 33, but going into 4.2.1 component selection and installation, actually I don't have anything highlighted in that, but I do have 4 highlights in the NEC requirements on page 34. NEC requirements 4.2.2, second bullet point's highlighted. Embedded cable shall be spliced only using splices identified in the manufacturer's instructions. You can only use their splices that they say you can use. Bullet point in the top right of the page is highlighted. Embedded cable shall be fastened in place by approved non-metallic means while concrete is applied. So usually that's your cable ties and stuff like that to fasten down those cables, zip ties. Next bullet point is also highlighted. Non-heating cable leads exiting the floor shall be protected by installing them in conduit. Non-heating cable leads exiting the floor shall be protected by installing them in conduit. And then the last bullet point of the page is also highlighted. Heating panels or panel sets shall not be installed where they bridge expansion joints unless provision is made for expansion and contraction. So you can actually see they had a picture of, I think that might have been in a previous section about how you actually show an expansion joint and what you have to use there. That is all my highlights for this chapter 9 or module 9, heat tracing and freeze protection. So you've got section 4 review, module review on pages 35 and 36. Supplemental exercise wouldn't be a bad thing to look at. And then of course your practice test. That's all I've got for this chapter. So let me know if you have questions.